Hi, I'd like for this video to cover a few things regarding integrals. So the first thing that we're covering here is it's asking us first to solve a definite integral. Remember that the distinction between a definite and indefinite integral is that indefinite integrals ask you to solve the integral where it doesn't specify the bounds. In this case, the bounds are specified, so we're actually going to have to first find the integral as if though we were finding the indefinite integral. And then at the end, we're just going to have to essentially use a formula that will allow us to plug in the bounds. So it'll take some arithmetic, but not too much. But when starting off with these problems, I always preface by saying, just go ahead and consider the indefinite integral version, which would just be without the bounds. Go ahead and solve this, and then at the very end, go ahead and do the whole plugging mechanism. So if you were to just take the integral of this, if someone gave you this as an integral to solve, the basic idea is you would look at that, you would break it down. So when you're taking integrals of several terms, you can take the integral of this, take the integral of this, and take the integral of this, and then just combine them by whatever operations were sort of binding them together. And so the integral of this would just be x cubed over 3 plus 2x squared over 2 minus 4x. So how did I get there that fast? Well, I just add 1 to the constant and I divide by whatever that exponent was after I added 1 to it. So if I had, x cubed plus 4x minus 2, and I wanted to take the integral of this, I would just add 1 to the constant or to the exponent and then divide by whatever that exponent is after it's changed its form. So, I'll sort of say this is x to the 4th. I'll add 1 to the constant, and then I'll divide by what that exponent now is. And then as I'm moving forward, I'm ignoring the constants. So this is a constant. I'm completely ignoring the constant. So in this case, I'll just say this is 4. And then just remember that there's a 1 here. So I'm going to add 1 to the exponent, and I'll divide by whatever that exponent now is. And then in integrals, if you're taking the integral of a constant, it doesn't go to 0 as it does in derivatives. It actually just becomes, you just tack on whatever you're taking the integral with respect to. So in this case, we're taking the integral with respect to x. So you tack on that x at the end. And then simplify if need be. And so a similar approach, or in fact, a completely identical approach, was used in this case to arrive at this as the answer. But the difference, so we evaluated this as though it was an indefinite integral, and we've arrived at this particular place. And so what we, and by the way, this may seem a little confusing. This is actually a 3. And we then signify that we are going to evaluate this at the bounds that were specified. So this is essentially what I'm referring to. And so what you do is you treat this as a function. So first you evaluate. So you do, if big F is your integral, then you're doing big F of 3 minus big F of 1. So this is the F is our integral. This is our integral, or you can actually take away these 2's. We'll just say it's x squared minus 4x. And we are now going to essentially plug in 3 and 1, and we're going to subtract them. So this would essentially be 3 cubed over 3 plus 3 squared minus 4 times 3. And then we're going to subtract the same thing, except we're now going to have to plug in 1. And so this would essentially be 27 divided by 3 plus 9 minus 12 minus 1 over 3 plus 1 minus 4, which this is, so 3 can go to 27 9 times, right? So we'll say this is 9 plus 9 minus 12 minus 1 over 3. And so actually we would want to be a little more precise about this. In fact, you probably want to plug this into a calculator, which I'll do now. So if you go ahead and plug this into a calculator, you would essentially arrive at 26/3, which actually comes about to being 8.66. So recap, you've taken the integral as though it was an indefinite integral. And then after doing that, what you've done is you've essentially evaluated the answer at 3 and 1, and you've essentially minused them. And so that's how that works. So on to the next question. So this next problem actually follows more or less the same pattern. We essentially only consider the integral, the definite integral, as though it were an indefinite integral without the bounds. And so we're reduced to essentially only sort of finding the integral of this, as it were. And so remember, the main rule is to add 1 to the exponent, divide by whatever that exponent then becomes. So we'll sort of follow that rule where we'll just say, okay, this is x to the -2/3. We'll add 1 to the top, which is the same thing as adding 3/3. This format, grabbing it from the denominator and then putting it top and bottom, allows us to both add 1, but it also allows us to do it in a very simple way where we can just sort of go across. And then we'll divide by whatever that exponent is. So what this exponent actually is, it's 1/3, right? Because -2/3 plus 3/3, if you sort of bridge that gap there, it's just 1/3. And so this essentially is reduced to being x to the 1/3 over whatever that exponent is, which is 1/3. And then once you're faced in a position where you have a over b over, let's say, c, the way out is to just say this is a over b multiplied by, or actually we're faced in a position where we have a over b over c, right? This is our a, this is our b, this is our c. And essentially what we do to get ourselves out of this situation is we say we'll take a, and then we'll sort of multiply a by the reverse of this. So this is c over b instead of b over c. And so the same idea is here, where we have x to the 1/3, just as we had that a there. And then we'll just multiply our x to the 1/3 as we multiplied our a by the reciprocal of whatever's going on in the bottom. So we'll just multiply this by 3/1, which is just 3. So we come out the other end with 3x to the 1/3. Now remember that, if you have x to the 1/2 is the same thing as under root x. So x to the 1/3 is actually the cube root of x. This 2 actually comes here implicitly. So in this case, the 3 would come here implicitly. And so we actually have 3 under root. We have 3 times the cube root of x plus c. That's our integral. But remember that we're evaluating this at 8 and 1. So we're going to have 8 here. We'll have 1 here. And so what we'll do is we'll say, okay, well, we'll first, for our x, we'll plug in the top bound, which is 8. And then we'll subtract that from, our integral. But in this case, we're gonna snatch that bottom bound, and so we'll have 3 times the cube root of 8. The cube root of 8 is 2 minus 3 times the cube root of 1, which is just 1. So we have actually we would have 6 minus 1, which is 5, which doesn't seem too right. Let's see here. I think we actually omitted a 1 in our process. If we sort of take a step back a little bit here, you can see that we have 3 times 2 minus 1, but I think we're forgetting the fact that back here we have 3 times under root 1. So this is 1, but then we still have that 3 there, right? That's 6 minus 3, which is then 3. So our answer is then 3. So more or less the same idea here, where we're considering the integral, the definite integral, as though it were a indefinite integral. So in this case, we have pi over 2. So well, actually, we'll just omit that for now. So we're just taking the integral of cosine theta d theta dx or d theta. So the theta may throw you off, but the idea is that this is the same thing as asking dx. So in this case, we're taking the integral with respect to x. In this case, we're taking the integral with respect to theta, where theta is just an angle. So it's really no different. If we know that the integral of cosine of x is sine of x, then the integral of cosine of theta is sine of theta. So this comes about to being sine of theta, evaluated at 0 to pi over 2. So we're going to take sine of theta, and we're going to evaluate it at the upper bound, which is 0, minus the lower bound, which is pi over 2. So sine of pi over 2. Now, sine of 0, right, at 0 degrees, what is the y value? Well, the y value at 0 degrees is 0. So because if you're on the x-axis, then your y values are all 0, minus sine of pi over 2. So this is pi over 2, and the y value at pi over 2, since we're on the x-axis now, is in fact 1. So our answer comes about to be -1. So in this particular question, again, we're sort of considering the case where you just have the indefinite integral of this particular problem. And we essentially, so we're looking at an integral where we have two terms, right? And remember that if we're looking at an integral where we have two terms or three terms or however many terms you'd like, you can essentially take the integral of the terms individually and then just combine them back together using whatever operations we're binding them. So in this case, well, you can take the integral of 2 sine of x dx, right? And you're just taking the integral of this. You can subtract that from the integral of e to the x dx. And this is something that you could do sort of in your head. It's more or less like, when we were taking the derivatives, if someone asked you to take a derivative of this guy here, this is the same thing as taking the derivative of the individual components. But most people don't actually write this out. It's sort of verbose to do so, but that's actually what's happening here. So you can treat these individually. So what's the integral of 2 sine of x? You could further simplify this down by pulling the constant out and just taking the integral of sine of x, because that's a thing, right? If you have a constant multiplied by a function and you're taking the integral of this, you can just pull the constant out and then just take the integral of the function. And that's what we've done here. We've pulled the constant out and we're just taking the integral of the function. The integral of e to the x is just e to the x, so we can take care of that while we can. So it's just 2 times the integral of sine of x. So what is the integral of sine of x? It's negative cosine of x minus e to the x, which we had as our residue, so to speak. So this is minus 2 cosine of x minus e to the x. But why did I say that that the integral of sine of x dx is negative cosine of x? But just remember, this is our answer for now. But why did I say that? Well, the idea is that this can only be the integral of this if you can take the derivative of the integral and get back the original function. So for instance, if I had x squared on this side, and then I had x cubed over 3 on this side, this is the antiderivative of this if I can take the derivative of this and get back the original function. And you can see that if I take the derivative of this guy here, I'll have 1 over 3 times 3x squared. The 3's cancel out, I have x squared. So I get back the original function. So I should be able to take the derivative of this and get back what I had before. Then and only then can it be the antiderivative. Then and only then do I have the right to call it the antiderivative. So what's the derivative of what's d over dx of negative cosine of x? Well, you sort of ignore the negative here. So it's just negative. What's the derivative of cosine? It's sine of x. It's negative sine of x. So this becomes positive sine of x. So you see how I got back the original. So this is an easy fact to remember, that the integral of sine of x dx is in fact cosine of x, except it's negative. So just keep that in mind. But back to what we were doing, we found that the integral of this is this. The antiderivative of this guy in here is this. And so we evaluate this from 3 to 0. So we're gonna say 2 cosine of x minus e to the x. We're gonna evaluate this at 3, the upper bound. and then 0 as well, the lower bound. So we'll say this is -2 cosine of 3, the upper bound, minus e to the 3, again, the upper bound, subtracting from the same thing, -2 cosine, the lower bound, minus e to the lower bound. What does this come out to be? Well, we're definitely going to leave this side as it is, in particular because we can't really evaluate e to the third or cosine of 3 without a calculator. But this portion, right? So cosine of 0 is 1, so we can sort of blacken that out here. So we have -2 times 1, which is -2, minus e to the 0. E to the 0 is 1. Anything to the 0 is 1. And so we have -2 cosine of 3 minus e to the third plus 2. Or actually not plus 2, but first let's actually solve what we have in here, minus. So what we have in here is -2 minus 1, which is -3. So we have -2 cosine of 3 minus e to the third plus 3. And of course, you can have this plus any. You could be here, you could be here. It doesn't matter so long as it exists. So we want to find the indefinite integral. In this case, it's not an definite integral, so we really don't have to match any bounds, or not really match, but we don't have to plug in any bounds. But interestingly enough, always a very dependable pattern is that when you're looking at an integral and you have multiple terms on top and you have one term on the bottom, it almost always is the case that it's easier to essentially break up the fraction by using the common denominator. So what I mean by that is, like, this integral here, it's not that hard. It's pretty hard to take, but if we simplify it to where we can sort of use the power rule and sort of make it look like a polynomial, then it can actually resemble something that we're familiar with. So I'll start by saying that, if I break this up individually by a common denominator, I can say that this is under root x over x plus x over x dx. Does that make sense? And then, this integral is the same thing as this integral. So actually, I haven't taken the integral yet. I've just sort of expressed the first as integral as the I've expressed the first integrand, the thing that's being integrated, as something else that is actually easier to look at and easier to take the integral of. But still, I can still do some things, right? For instance, one thing that I notice is, I can't really do anything here, but x over x is just 1, so I can make this 1 here. So this integral and this integral are the same. I'm just expressing it in better ways. And instead of having a fraction here, there's a 1 here. What I can do is I can say this is 1 over x plus x to the 1/2. Remember that under root x is x to the 1/2 multiplied by x to the -1. Because when I take this x up here, it becomes negative. And that's true for any number. If it were 1 over x squared and I were to take it up to the top, it would be x to the -2. So I have this as well, and I have plus 1 dx. So this and this are essentially the same. They're the same integrand. I'm just sort of expressing it in a different form. And if I want to combine this, if I want to do x to the 1/2 times x to the -1, the rule is that you essentially add the exponents. So you would actually be doing 1 over 2 plus -1, which is 1 over 2 minus 1, which is the same thing as 1 over 2 minus 2 over 2, which is -1 over 2. So this is the same thing as 1 over x plus x to the -1 over 2 plus 1 dx. And again, I mean, I haven't terribly changed the the thing that I'm taking the integral of is still, it's still the same thing. It's just that I've expressed it in a different form, and I can actually take I can take the integral now and do the anti-derivative process. And so what I'll do here is I'll break this up. I'll say that this is 1 over x dx plus the integral of x to the -1/2 dx plus the integral of 1 dx. So I know that the integral of 1 over x is just ln of x. Plus, I'm going to add 1 to the top, so I'll do x to the negative 1 over 2 minus 2 over 2, divide by whatever that is. So that I actually want to add 1, right? So I'm not going to subtract 1, I want to add 1. So I'm going to say this is 1 over 2, right? Because this comes about to being 1 over 2. I bridge that gap and I see that it's 1 over 2. Plus, so if you're taking the integral of a constant, it's just that constant tacked on with whatever you're taking the integral with respect to. So if it was a 2 here, I would have tacked on an x, but it's a 1, so I'm just going to say x. So I have ln of x plus, so this is what, right? This is x to the 1 over 2 over 1 over 2 plus x. And I'm going to actually reverse this. So I'll say ln of x plus, so remember, I essentially, if I have x to the 1 over 2 over 1 over 2, I can actually just multiply x to the 1 over 2 by the reverse, which is just 2. So I'll say this is 2x 1 over 2, 2x 1 over 2 plus x. And remember that the x 1 over 2 is actually under root x. So this is ln of x plus 2 under root x plus x. And so that's plus, yeah, I guess if you, well, yeah, if we're talking about the indefinite integral, then this would essentially be your answer. So we essentially want to treat this problem more or less the same way we've been treating the others, where we only consider the version of the definite integral that we've been given, except we're just sort of considering the definite integral, but we're treating it as a indefinite integral for a little bit here. And the idea is that, like, you're just taking the integral of this, you're taking the integral of this, you're taking the integral of this, and then you're just combining that together. The integral of a constant is a constant, so we'll just leave that as 1 over 8, except, you tack on whatever you're taking the antiderivative with respect to, which in this case is w, and then plus, so you're essentially ignoring you're ignoring the constant, and so then you're taking the integral of this this w here. So we add 1 to the top, and then we divide by whatever our exponent is now. So this is what we have here in the middle, and then we'll add. So we ignore the constant again. We'll add 1 to the top, so we'll say w 1 over 3 plus 3 over 3. We're adding 1 to the top, divided by whatever that exponent is. So now this exponent is actually 4 over 3. So here we have 1 over 8 times w plus, so we have w squared divided by 4 plus 1 over 3 multiplied. So what do we have, right? What is this component here? So we have w 4 over 3 over 4 over 3. So we take our w 4 over 3 and then we multiply it by the reverse, which is 3 over 4, which essentially gets us 3 w 4 over 3 over 4. So we have 3 w 4 over 3 over 4. And so we have 1 over 8 w plus w squared over 4 plus, and so our 3's cancel out, and you could see this as if you had combined them. 3 times 4, these 3's would just cancel out. Or you could think of it as, what if you didn't do that? What if you had 3? What if you multiplied these? You'd have 12 in the bottom, right? And then this would cancel out with this. 3 can go to 12 4 times, and you still have a 4 in the bottom. So you would still be left with this component regardless of how you would do it. So yeah, in every case you have the same thing. But anyways, the point stands that we have w 4 over 3 over 4, and that's our integral. That's our integral. But remember, we want to evaluate it at 8 to 0. So 8 is our upper bound, 0 is our lower bound. So we're gonna plug in our upper bound, 8 plus. So we plugged in our upper bound here, 8 squared over 4 plus you could think of this as 8 to the 4 over 3, and we'll get to that, minus had we plugged in a 0. So if you plug in a 0, you'll get 0 plus 0 plus 0. So all of this will go to 0. So really our only concern is to solve this part. And our 8s cancel out. 64, right? 8 squared is 64. 64 divided by 4. 4 can go into 64. 4 can go into 64 16 times. So we took care of this guy as well, because essentially this came about to being 64 over 4, and 4 can go into 64 times. 4 can go into 64 16 times, so we said this is 16. 64 divided by 4 is 16. And then so here we deal with this. How do we deal with this? So 8 to the 4 over 3 is the same thing as 8 to the 1 over 3 to the times 4. So this is 8 to the under root to the 4th power. Under root, the cube root of 8 is 2 to the 4th power. Let's see here, which is 16, right? Because 2 times 2 times 2 times 2 is 16. So you have 16 divided by 4. So this is 16 plus 4 can go into 16 4 times. This is 20, right? Plus the 1 that we had here, because when we cut this 8, we're left with 1. So we have 1 plus 20, so it's 21. So in this case here, we're sort of repeating the same pattern where we essentially only consider the version of the definite integral where it's only sort of a indefinite integral. And when we solve this question, so from 2 to 1, right? We'd break it up first, right? We would say this is the integral of 1 over x squared dx minus the integral of 4 over x cubed dx, right? And then we're sort of solving these individually. And the first thing that I noticed is that you could take this to the top, and this would be the integral of x to the negative 2 instead of the integral of 1 over x squared. And what that does for us is it simplifies it. Now we can use the power rule of integrals on this particular portion. And the same thing can be done here, right? We could say that instead of 4 over x cubed, we can say this is 4 to the x to the negative 3rd. And why am I doing that? Because it allows me to use the power rule of integrals. I can then go back and just add 1 to the top here. I can say this is x to the negative 2 plus 1, and I'll divide by whatever that is, which is negative 1. And then I can do the same thing here. I'll ignore the constant. I'll add 1 to the top. I'm adding negative 3 plus 1. I'll divide by whatever that is, which is negative 2. And so I have negative x to the negative 1 minus the negative 2, right? Or if that was a little too fast, I apologize. Negative. So what would happen in this case is this would be 4x to the negative 2 over 2, right? Negative. So this would be negative x to the negative 1 minus, well, these minus will be positive, plus 4x to the negative 2 over 2, right? And now I can sort of simplify this. I can say this is negative x to the negative 1 plus 2x to the negative 2, which is negative x to the negative 1 plus, well, you can essentially think of this as 2 over x squared is essentially a good way to think about it. And then you'll have negative 1 over x plus 2 over x squared. So this is like our final integral, really nothing we can do beyond this point. But sort of going back up here, we're supposed to evaluate at 2 and 1. So we'll sort of evaluate this at 2 and 1. And we'll say, okay, well, let me go ahead and plug the upper bound, which is 2 plus 2 over 2 squared, right? Subtract that from plugging in the lower bound, which is negative 1 over 1, right? Because we're plugging in this lower bound, plus 2 over 1 squared, right? And so what you notice is that this part, negative 1 over 2 plus 2 over 4, which is actually 1 over 2, 1 over 2, -2 over -1 over 2, this sort of goes to 0, minus, so we have -1 plus 2 over 1, which is just 2. So this essentially comes about to being negative -1 plus 2, which is 1, but then it just becomes -1. So let's go ahead and take a look at this integral here. So again, let's just consider the case without the bounds, and we're looking at under root t minus 3 cosine of t dt. And again, we can split this up, right? We can just take the integral of this dt and sort of just take the integral of this. Just a sort of side note, right? So, when we were taking the integral of sine of x dx, we said that this is negative cosine of x because we actually had to take the derivative of this and get this back. And so the integral of sine of x is negative cosine of x. But if we're taking the integral of cosine of x dx, then this is what, right? This would just be sine of x because the derivative of sine of x gives you back the original function. So sine of x is the integral of cosine of x. Whereas negative cosine of x, if you take the derivative of this, you would have negative sine of x, which is sine of x. So just, if the reasoning isn't too apparent, then I suppose to cram up these facts is useful. So taking the integral of this part here, this is the same thing as t to the 1/2 dt, right? Minus what we have here. And again, we said that the integral of cosine of x or cosine of t or cosine of z is just sine of t, z, or d, or whatever. So it's just 3 sine of t. And in this case, so we'll add 1 to the top, right? We'll do plus 2 over 2 and divide by whatever that exponent is, which is 3 over 2, minus what we had before. And of course, so this is t 3 over 2 over 3 over 2 minus 3 sine of t, right? And the idea is that, you can multiply this by the reciprocal of this. So you have t 3 over 2 times 2 over 3 minus 3 sine of t, right? Which is just 2t 3 over 2 over 3 minus 3 sine of t, and that's our integral, evaluated at pi over 2 and 0. So pi over 2 and 0. And so if we plug pi over 2, what do we get, right? So it's 2 pi over 2 cubed, right? Or you can just leave it as it is. It's just pi over 2, 3 over 2, over 3 minus 3 sine of pi over 2. Now, sine of pi over 2 is 1, so that's just 3 here. And we're going to subtract, we're going to plug in 0 into this same function, right? So if you plug in 0, you actually get, plug in 0 here, you get 0. You plug in 0 here, sine of 0 is 0, so that 3 is affected by that. So you just get 0. So this essentially just would be your answer. So this question here, I guess, sort of kind of looks intimidating, and the goal is to sort of put this in a form where it's just an even polynomial, and we can actually, sort of use the power rule on it a couple times. And so we're just gonna, for now, consider this, where we have 3 under root x plus 4 under root x, and then dx. And then we're gonna, so I can rewrite each of these as x to the 1/3 plus x to the 1 over 4, right, dx. I mean, that's true for anything. Like if you had 9 under root x squared, right? So the 2 would go in the top and this would go in the bottom. You could rewrite that as x to the 2 over 9. Or if you had x to the just 9, there's a 1 here, right? So the 1 would go in the top and then the 9 would come to the bottom. That's what I'm doing here, right? I know there's a 1 here, so just rewrite this as 1 over 3 and 1 over 4. And I'll go ahead and distribute this so it's like an even polynomial. So I'll do x times x to the 1/3, and I'm still just rewriting the integral. I'm not actually taking the integral yet. So I'm doing x times x to the 1/3 plus x times x to the 1/4 dx. So the rule is like if you're doing x to the a times x to the b, this is equal to x to the a plus b. So with that in mind, we're essentially doing 1/3 plus 1/3 plus 1, which is the same thing as 3/3, which is 4/3. So this is actually x to the 4/3 plus, so same thing, right? 1/4 plus 4/4, which is 5/4. So this is x to the 5/4 dx. And with that also in mind, now we sort of can take the integral of this particular function or of the integrand. And so we'll add 1 to the top and divide by whatever that top is. So we'll say x to the 4/3 plus 3/3, which is going to be 7/3, right? So we'll put that in the bottom, plus x to the 5/4 plus 4. So if we add 1 to that, we know that's so 5/4 plus 4/4, right? And what that would be is it would be 9/4. So what we have as an answer is x to the 7/3. And if you were to play this out, you would just multiply by the reverse. So you would actually have, instead of 7/3 to 3/7, plus you would have x to the 9/4, right? And then you're multiplying by the reciprocal. So instead of having 9/4, you'll have 4/9. And this is your integral, right? Evaluated at 1 and 0. So 1 and 0. So you're plugging in. So let's go ahead and plug in 1. So we'll do 3, 1, 7/3/7 plus 4, 1, 9/4/9. And then we're going to minus the lower bound plugged into the same function, which if you plug it in, you'd have 0 and 0. So you're just doing 3/7 plus 4/9, which is 63. 9 times 3 is 27. 7 times 4 is 28, which is 50. I think it's 54/63. 27 plus 28, 55. So 55/63 is your answer. So with this particular problem, again, we'll consider the integrand or taking the antiderivative as if though it were an indefinite integral. So we'll say this is x/2 minus 2/x dx. And so what would you do in this case? Well, let's try to make this into a polynomial or simplify as much as we can. The first thing I notice is that I can rewrite this as 1/2 times x minus, I can actually rewrite this as 2 times 1/x, right? And so this is one part, right? And this is one part. And so I'm essentially taking the integral of 1/2x dx minus the integral of 2 times 1/x dx. I can actually pull these constants out too. As I can say, this is 1/2, just the integral of x, minus, I can pull that constant out as well, 2 times, or just 2 times the integral of 1/x dx. And so the integral of x, so you see how like this is what we were given, and now because we've sort of rewritten this process, all we have to really do is take the integral of x and 1/x and then just multiply them by their constituent constants. And so this is 1/2, right? X in this case is what? The integral of, so that's just x squared over 2, the integral of that, minus 2 times the integral of 1/x, right? So that's 2 times ln of x. So remember that the integral of 1/x dx equals ln of x. So this is just x squared over 4 minus 2 ln of x evaluated at 2 and 1. So 2 as your upper bound, 2 as your lower bound. So, we'll say this is 2 squared over 4 minus 2 ln of 2 minus 1 over 4 minus 2 ln minus 2 ln of 1, which is 1 minus 2 ln of 2 minus 1 over 4 minus 2 ln of 1. So ln of 1 is actually 0, as it turns out. So this is 1 minus 2 ln of 2 minus 1 over 4. Yeah, I think that makes. And of course, if you're particularly for it, you could sort of simplify this, right? You could combine this, right? You could say this is 1 minus 2 ln of 2 minus 1. And then you could distribute. You could say this is 4 minus 8 ln of 2 minus 1 over 4. And then maybe you could spread it out again and say this is 4 over 4 minus 8 ln of 2 over 4 minus 1 over 4, which is 1 minus 2 ln of 2 minus 1 over 4. And then perhaps you could combine these and say this is 1 over 4 plus 4 over 4, which is 3 over 4. So this would reduce to 3 over 4. You'd say this is minus 2 ln of 2 plus 3 over 4, or inversely, you could say this is 3 over 4 minus 2 ln of 2. And that would essentially be your answer. So with this particular question, it's a U substitution problem. So we treat U as negative x squared. And the basic idea here is that, so if the idea is that U is equal to negative x squared, and then we take the derivative of U. So du over dx, if we're taking the derivative of U, is equal to negative 2x. And then we actually use dx and du as if though they were algebraic components. And so I'm going to essentially multiply both sides by dx. So I'm left with du equals negative 2x times dx. And then I'm going to isolate the dx. And I know it looks weird, but I'm going to say dx equals du over negative 2x. So I divided both sides by negative 2x. So I have this component. I have two things. U is equal to negative x squared, and dx is equal to du over negative 2x. So when I'm looking at the integral of x e to the negative x over 2 dx, I can replace this with the u, and I can replace the dx with what I solved for. So, with that in mind, I can say that this is actually equal to, I have my x times e to the u. Remember, u is equal to negative x squared. And then dx is replaced with du over negative 2x, so du over negative 2x. And which, if I extend this fraction, I'll have x times e to the u over negative 2x du. The x's cancel out, so I'm left with the integral of e to the u over negative 2 du. I can actually take this negative 2 out, so I'll say this is 1 over 2, negative 1 over 2, e to the u du. And essentially what happens, right, is that, the integral, we covered this before, the integral of e to the x is e to the x, and the same way the integral of e to the u is e to the u. So this would just be negative 1 over 2 times e to the u, which is e to the u over 2, right? And what we can then do at this stage is just plug back what u was, which was negative x squared. So this is e to the negative x squared over 2. So with this problem, it's best to sort of rewrite this as saying that this is cosine of theta to the third sine of theta d theta. So for instance, if you have like secant squared x, right, this is actually secant of x squared is what this notation is representing, or the same thing, you have cosine of the fourth. It's the same thing as cosine of x to the fourth. So the same idea is utilized here, and then it's clear to see that u should be the inner piece here, which is cosine of theta. And then with that angle, du over du over d theta would essentially be negative sine of theta, negative sine of theta. And essentially, if we were to isolate, so we would multiply d theta, right? Because we want to represent this piece, we want to sort of take it out of the integral here. So we'll multiply both sides by d theta. D theta cancels out. Du equals negative sine theta times d theta. And then if we were to sort of, if we were to isolate d theta, we would have d theta equals du over negative sine theta. So these are our two sort of pieces here that we're gonna. So we had the integral of cosine raised to the third power of theta. So sine theta d theta, and then we turned this into. So we said that this is u to the third, and then sine to the third, and then we represented d theta as being du over negative sine theta. So du over negative sine theta, which is u to the third sine of theta over negative sine theta. These canceled out, so we're left with the integral of u to the third over negative 1 du. And so this is what? This is negative u to the third du. We add 1 to the top, u to the fourth over 4. And then we'll sort of replace our u with what we had as cosine theta. So negative cosine of the 4 theta over 4 plus c, the constant of integration. And that's our answer. So in this problem, we let u equal to ln of x. And so we're letting u equal ln of x. And with that in mind, so we let u equal ln of x, so du over dx will equal ln of x, or sorry, the derivative of ln of x, which is 1 over x. And then we'll multiply both sides by dx, right, to isolate that dx. So du equals dx over x. And at this point, perhaps we would want to sort of isolate the dx, so we'll multiply both sides by x. And then we have x du equals dx. So we were able to, so u is ln of x. So basically, this here, this part becomes the u. So we have u squared over x. And then the dx is replaced by this guy here, which is x du. Which is the same thing as u squared over x du. These cancel out. So you're left with just u squared du, which is u cubed over 3, the integral of this, right? Add 1 to the top, divide by whatever that exponent is. And then just sort of put back the u that you had, which was ln of x, right? Which would just, in this case, be cubed over 3. And then, of course, the constant of integration. So this problem here, so we let u really equal the complicated thing, which is 2 plus 3 er, because see, if u equals 2 plus 3 er, then we can say that this is u 3 over 2, right? So it's clearly indicative of the fact that u should be something that we can then transform into using the power rule. And so we let u equal 2 plus 3 e to the r. And so once we're at this stage, we can then say that du over dx, which is the derivative of this, will equal 2 plus, well, 2 goes to 0, 3. So this is 3 er. So what we were doing right now, we were taking the derivative of 2 plus 3 er. The derivative of this is 0 plus 3. The constant comes out. E to the r, so what's the derivative of e to the r? Well, we know that e to the x is e to the x, so e to the r must also just be e to the r. So we just said that this is 3 e to the r. So du over dx is 3 e to the r. And if we're solving for dx, first we would probably isolate it by getting it on this side. Then we'll divide both sides by 3er. So dx equals du over 3er, right? And so this is one component. This is another component. So we can replace this and we can replace this. So we have e to the r 2 plus 3 e to the r 3 over 2 dr essentially becomes, so we replace this with a u, right? This is still here, e to the r. We replace this with a u. And then dr, dr, let's see, this should have been an r, right? So dr will just be du over 3er. So it's du over 3er, which is the same thing as e to the r u 3 over 2 over 3er. The er's cancel out. We're left with the integral of u 3 over 2 over 3 du. And then we'll pull the constant out. We'll say this is 1 over 3, the integral of u 3 over 2 du. And at this point, well, we have 1 over 3. We'll add 1 to the top. We'll say this is u 3 over 2 plus 2 over 2 over whatever this is, which is 5 over 2. So this is 1 over 3 times u 5 over 2 over 5 over 2. And we know that we essentially multiply this by the reciprocal. It's 1 over 3 times u 5 over 2 times 2 over 5 this time, right? Because we're just multiplying by the reciprocal. So this just becomes 2u 5 over 2 over 15. And then, of course, you can just plug the u back in to here. And then, or actually to here. And then you'd arrive at your final answer, so to speak. But that process is pretty much consistent. So we would let u equal the thing that is not letting us take the integral quite easily. We'll say that actually, before we actually do this, you can see that this is a definite integral. So we're going to actually have to use the whole plugging thing after we're done here. But for now, we'll just consider that this is cosine of pi over 2. Or actually, it's pi t over 2 dt. So we're just sort of temporarily ignoring these bounds. And so we can say that this is, so we will essentially let u equal pi t over 2, kind of odd, pi t over 2. And then if we take the derivative, du over dt, right? Remember that, so just recall that pi is constant. It's a constant. So just like you can pull out the numbers, you can also pull out pi because pi is constant. So du over dt is the derivative of this, so we essentially want to take the derivative d over dx, or well, in this case, dt of pi t over 2, right? So this pi over 2, this is a constant. Pi is a constant, 2 is a constant, just like 1 over 2 is a constant. You can pull both of them out. In this case, we're just pulling pi over 2 out. So this is actually pi over 2 times the derivative d over dt of t, right? So, and the derivative of t is 1, just like the derivative of x is 1. So we're just left with pi over 2. So this whole thing just goes to 1, right? So d over dt, and then we'll solve for dt. Du equals, so we have dt pi over 2. And then, you can just leave it like this times pi over 2, right? That, and then we'll just divide both sides by pi over 2 to get rid of the dt, or to get rid of the pi over 2 to get the dt alone. So dt equals du over pi over 2. which is we multiply by the reciprocal, right? So that's du 2 over pi. So we multiplied by the reciprocal. So this is dt. So we can replace this part with this, and then we can replace u. So basically, the integral of pi t over 2 dt just became the integral of cosine of u, right? Du over, so dt we replaced with this, right? Which is, so dt equals 2 du over pi. So 2 du over pi, which is the same thing as 2 cosine of u over pi du, right? We can pull this part out, it's a constant. So we'll say this is 2 over pi, the integral of cosine of u du, which is then, so then we're just left with doing the integral of pi of cosine of u, which is sine of u, right? And yeah, so this is 2 sine of u over pi. What was u? U was pi t over 2. So this is 2 over pi times sine, this is, or 2 sine of pi t over u, right? Over pi. That's our integral. Pi t over u, is that? Let's see here, sine of u, sine of u. Let's back up a little bit here. So we have 2 pi times sine of u, which is 2 sine of u over pi. Yeah. And then our u was pi t over 2. So that's 2 times sine of pi t over u over pi. Let's see here. Yeah, so when we're replacing the u part in here, the u is actually pi over 2, pi t over 2, not pi t over u. So it's actually pi t over 2. And so that's our integral, right? And then of course this is evaluated at 1 and 0, so 1 and 0. So that would essentially just be 2 sine of pi over 2 times 1 over pi. Let's see here. Yeah. And of course, so this would just be pi over 2 times 1 is sine of pi over 2, right? And sine of pi over 2 is just, let's see here, on the unit circle, sine of pi over 2 is 1. Sine of pi over, so this is just 2 over pi, right? Because this goes to 1, because sine of pi over 2 is 1. So this is just 2 pi minus, so we plug in 0 into the same function, right? So that's 2 times sine of pi over 2 times 0, right? Over pi. Now, this is 0, so this becomes 0 as well, because these multiply. Sine of pi over sine of 0 is 0, right? Pi over 2 and 0, they multiply, so this becomes 0. And then 2 times 0 becomes 0. And 0 over pi becomes 0. 0 over anything is 0, so this is 0. And so this is your answer. So let u equal 3t minus 1 du over dt equals 3, and then du equals 3 dt. Divide both sides by dt, and then you'll have du over dt equals, or sorry, you'd have du over 3 equals dt. So we can then replace the t by du over 3, and then the u can essentially take the place of all this. So this will just be u50 du over 3, right? So du over 3, which is same thing as 1 over 3 u50 du, which is 1 over 3 u51 over 51. So what does this part become? 51 times 3. It's u51 over 153. And then if we plug the 3t minus 1 back in, 3t minus 1 to the 51 over 153, evaluated at 1 and 0, so 1 and 0. And then what we'll do is we'll do 3 times 1 minus 1 to the 50th 1 power over 153 minus 3 times 0 minus 1 to the 51, which is 0 to the 51. Well, actually, yeah, it would be negative 1 to the 51, actually, which would be 150, and then over 153. And then I'll leave it to your discretion to do that. So for this problem here, we often let u be the exponents when we're working with e to the something. So let u equal 1 over x. And then du over dx, we're taking the derivative of 1 over x. So the derivative d over dx of 1 over x is what, right? So again, let's put this in a form that's easier for us to understand, which is x to the negative first. And so now we can actually use the power rule. We'll bring this down. We'll subtract 1 from the top. So negative 1, x to the negative 2. Which is negative x to the negative 2. So du over dx equals the derivative of this, which is negative x to the negative 2. So if we isolate dx, du will equal negative x to the negative 2 times dx. And we'll divide both sides by dx. Well, actually, we'll divide both sides by negative x to the negative 2 because what this allows us to do is it allows us to isolate dx, and then we'll replace this piece here. So dx equals du over negative x to the negative 2. So we have x to the negative 2, right? Which is 1 over x squared, right? If we take that to the bottom. So we have du over negative 1 over x squared. So dx becomes du negative d, so we multiply du by the reciprocal of this, so which is x squared, right? So dx will actually equal negative du times x squared. So we replace this portion with this. So this becomes e to the 1 over x squared dx. We replace this part with a u and this part with du, so this becomes e to the u over x squared, and then this dx here we replaced with negative du over negative du times x squared, so times negative du times x squared, right? This is the component that we replaced with. So this is negative e to the u x squared times x squared du, right? Just sort of reforming this so it matches what we regularly see in terms of the format for integrals. These x squareds cancel out. We're just left with doing EU. And the integral of e to the x is e to the x, just like e to the u is e to the u. So this is just negative e to the u. And with that said, we can then substitute 2 and 1, right? So we'll do negative e to the 2 minus e to the 1, right? Actually, let's see here. Maybe something's a little off. Yeah, so we replace our u with 1 over x, right? So negative e to the 1 over x is our answer. And so this is evaluated at 2 and 1. So 2 and 1. So we do negative e to the 1 over 2 minus let's see here, minus e to the 1 over 1, which is just e, so negative e or we can make this an under root plus e. And that would essentially be our answer. You could say that e negative under root e. Same idea, right? Same idea.